1 charge tape. And the purpose of this lab was to find the amount of charge accumulated on a charged object tape. We used Newton's second law as well as an understanding of charge interactions, so like charges repel, opposites attract, and that charge can be transferred via friction, free body diagrams to model forces on a system, and Coulomb's law to find the magnitude of an electric field and the force due to that field. The charges on each tape were found to be equal at 9.33 times 10 to the negative ninth coulombs, so that's my results. The procedure involved charging two tapes, so we ripped our experimental tapes off of our base tapes in order to ensure that our experimentals had a positive charge. Then we placed tape 1 slack across vertical objects, brought tape 2 below tape 1, and because the two tapes were charged in the exact same way, the tapes have an equal charge and are both positive, so they repel, and therefore the force due to the electric field of tape 2 is directed upwards on tape 1. So tape 1 moves upwards at an assumed constant velocity. So our system was tape 1, our surroundings were everything else, and the forces on the system was our force due to the electric field of tape 2, which is upwards, and then our downwards force due to gravity. We are ignoring air resistance here, and we know that Newton's second law says that the net force is equal to mass times acceleration. So some data and constants, the distance between the tapes at which point floating was observed, so when tape 1 started moving upwards, was 0.02 meters. Density of tape is 1 gram per meter. The length of tape 1 is 0.2 meters, and our constants are as follows. So using Newton's second law, we know that sum of F forces equals ma, and our electric force is kq1 q2 over d squared. So that's charge, which is q1, times the electric field of tape 2, which is kq2 over d squared. And we also know that using Coulomb's law. So the gravitational force is mg. Then we know that the sum of forces is the electric force minus gravitational force because they are in opposite directions. Our net force is 0 because our tape 1 is moving at constant velocity, so acceleration is 0, and therefore electric force equals gravitational force. Our mass is density times length, and then we multiply that by the acceleration due to gravity constant to get our gravitational force. And then our electric force, because Q1 and Q2 are equal, the charges on both tapes are equal, we know that kq1 q2 over d squared is just kq1 squared over d squared, and we already know k and d, so we can find electric force equals some constant, which is here, times q1 squared. So setting these two, EF and GF, equal to each other, we can solve for Q1 pretty easily. Just divide this constant, 2.25e13, divide that from 0.00196, and then square root that to get our value. The assumptions and givens are that the charges on both tapes are equal and evenly distributed, so tapes can be treated as point charges with their charge concentrated at the center of mass, and then all the givens from the experiment still hold true. So my code here shows that I create two objects, tape 1 and tape 2, which are spheres, so point charges, and then I set their positions so that the distance between them is still 0.02 meters. I find the mass of the tape, so that's still length times density. Then I find a function, gravity force, where it takes in the mass and returns the force due to gravity. And then I use the find charge function to take in two objects and the electric force between them, assuming that the charges on each object are equal. And I find the distance between the two objects, and then I solve for the charge squared. So I take that electric force, I multiply by the distance squared, and I divide by k. So I'm just sort of solving for charge based on the formula I showed you earlier, and then I square root that charge squared variable to get the charge. Now in lines 24 and 28, I visualize the gravitational force and the electric force using arrows, and then I call the find charge function using the objects tape 1 and tape 2, and with the electric force equal to the gravity force, taking in the tape mass as the mass. So the charge calculated by my function is the same, 9.33 times 10 to the negative ninth coulombs. And in this visual, we see that the cyan point charge is tape 1, magenta is tape 2, the yellow arrow is electric force, green arrow is gravitational force, the arrows are equal. What if the charges on electrons and protons were switched? Well, the tapes would still repel each other, but they would just be negatively charged. They would interact with other objects in the same way, but the direction of the electric field of tape 2 on tape 1 would be downward. The direction of the force, however, would still be upwards because we're multiplying by that charge, and charge is negative. So it would switch the direction, and so the tape would still float. It is important to handle the charge tape as little as possible because when the tapes meet your hand, some electrons are transferred from your hand to the tape. so that neutralizes the charge on the tape, which is not good. So some sources of error, not accounting for air resistance, measurement mistakes in distance or the tape length, and treating the system like a model, which it is not. So the tape is not a point charge, and the tapes do not have the exact same charge because they are handled differently. Our results, again, charge was 9.33 times 10 to the negative ninth coulombs, and overall conclusions, opposite charges attract, like charges repel, a charged object is attracted to a neutral object, charge can be transferred via friction, and then assuming model conditions, we can solve for charge.